Good day, I'm Norman Wobbeger. In today's video, we want to connect this problem that we're having with unique factorization of z with the original understanding of Euclid. This is, after all, a result that goes back more than 2,000 years, that every natural number n is uniquely factorizable into primes. Yet we have seen a lot of evidence for this claim that the number z, which is 10 triangle 10 plus 23, cannot in fact be factored into primes. So we have a logical conundrum here that we want to somehow resolve or point out, like, where is actually the problem. But first, let's actually solidify this claim and just make sure that we really believe that this is very, very plausible fact. So what do we know so far about z? Well, we have established, at least some viewers have established, that we have certain interesting prime factors. 3, 13, 139, 163, 18,301, 400,109, and this number 27997373. These are all prime factors of z. And then, of course, there's some remaining quotient. Let's call it w. And the natural question is, what can we say about this w, this quotient that we get when we take our number z and we divide it by these few prime factors that we have found? Okay, so let's proceed here in a number of steps. Let's sort of start with the simplest case. If we just look at 1 over 3, have this first prime factor here, and think about dividing z by 3. Now z is equal to 1 plus a huge number of zeros and then a 2, 3 at the end. So when we divide that by anything, it's a lot like taking 1 over that thing that we're dividing by, because we're effectively dividing 1 by whatever if we ignore that little 2 and 3 that are far at the end of this sequence. So as a first approximation, we can think about 1 over 3. That's, of course, the repeating decimal 3 repeated. 1 over 3 times 13, that's 1 over 39. That has a repeating cycle of 0.025641. The next one, 3 times 13 times 1 over 39, the reciprocal of that, so 1 over 5,421, has a decimal expansion that begins like this. 0, 0, 0, and then 184467810367009, and then it kind of carries on in some fashion or another. But how does it carry on? That's an interesting question. So correspondingly, if we take z and we just divide by the first 3 factors, then we expect to get a decimal number, very huge one, which at least begins with a 1844678 and so on. And then its subsequent digits have a lot to do with the reciprocal of this number here. All right, so let's try to get some understanding of what it means when we divide z by 3 times 13 times 139. So we're going to look at this problem of 1 over this number m. Then the phi function of m, the Euler-Toscan function, is 1 less than this times 1 less than this times 1 less than this, because this is a product of primes, and so the Euler-Toscan function is the product of the Euler-Toscan function of each one of those, and each one of those, the Euler-Toscan function is just 1 less than it because it is a prime. So this thing turns out to be 3,312, which has this factorization. And this is important for us in that it determines the order of this group U of M. Okay? And it's in this group U of M that the powers of 10 are playing themselves out, and it's the order of 10 in this group which determines the length of this repeated cycle in the decimal expansion of 1 over m. So to find that order, let's have a look at 10 to various factors or divisors of this phi of m. First of all, we can check using our computer that if we take 10 to this full power, then we do mod m get 1. That's a statement of Euler's theorem, because m, which is this number here, and the number 10 are relatively prime. They have no common factors. So 10 to the phi of m should be congruent to 1 mod m. Okay, so that's one possible exponent that will give us 1. But we're interested in what's the smallest such possible exponent that gives us 1. So what we can do is try different factors. We can, for example, say remove that 23 and see what happens. If we take 10 to the 2 to the 4th times 3 squared mod m, we get 2536, which is not equal to 1. Okay, so that's not going to work. But how about reducing the power of 3 from 3 squared to 3? Well, that turns out to give us 1. But if we reduce it 1 further by just removing the 3 altogether, then we don't get 1. So we can reduce the 3 from 3 squared to just 3. And what about reducing the power of 2? Well, if we take 2 squared, we get 1. If we take just 2, we get 1. But if we drop the 2 altogether, we get something that's not equal to 1. So the smallest exponent that we can use, which is a factor of this, will be 2 times 3 times 23, which is 138. And this way we establish that the order of 10 in the group U of M is 138. And that's also telling us that the length of the repeated cycle in the expansion of 1 over m will have length 138. So what actually does happen? Well, if we look at the reciprocal of 1 over 3 times 13 times 139, our computer can actually expand that out to many thousands of digits, no problem. And by looking at that, we can write down the decimal expansion up to the place where it starts to repeat. Find that place where it repeats, right about here. Then we have 1, 8, 4, 4, 6, 7, 8, 1, and so on. And then if we count the number of digits in this cycle, we find that there's exactly 138 of them, as we've predicted by that calculation in the group U of M. So this is telling us what actually the quotient z divided by 3 times 13 times 139 looks like as a decimal number, or as a numeral, starting from the left. Okay, so it starts like this, and then here it will repeat another 138, exactly the same sequence, and then another 138, exactly the same sequence, and so on and so forth. So it'll just keep on repeating that all the way to the end, almost to the end. At the very end, something a little bit different happens because the cycle might not go through an exact sequence, and we also have to take care of the 23 that distinguishes a z from a pure power of 10. So I'll leave it to you as an interesting exercise to figure out how many such repeating cycles are there in the expansion of z over this. How many of these repeating cycles are there? And what does this last cycle look like, which is a little bit different from the other ones? So we see that the quotient is pretty complicated, but it's not, beyond understanding. But there's a fair amount of complexity contained in this cycle of 138. You need that much information to sort of encode it, as well as this additional information of how many of these things there are and what does the last cycle look like. So it's a little bit complicated, but not out of the question to sort of get your head around it. But what happens when we up the number of primes? Okay, so let's take the product of all the primes that so far we know divide z. Let's call this m now. So it's the product of all of these primes that we've talked about. Then phi of m is going to be the product of 1 less than each one of these primes. And that turns out to be this number here, with factorization given like this. So we can now ask, well, what is the length of the repeating cycle if we take 1 over m? It will also have a repeating cycle. And how long is that repeating cycle? Well, that's a little bit more subtle now because the problem is a little bit more complicated, but it's essentially the same idea. We're going to look for the order of 10 in U of M. In other words, we're going to ask ourselves, what power of 10 do we need to get something congruent to 1 mod m? Now our computer can actually deal with this very efficiently. So if we take 10 to this whole number, mod m, we're going to get 1. But what we can do is we can start dropping some or more of these prime factors. We can say try removing this one and seeing if we still get something congruent to 1. Or we could start maybe removing one of these powers, maybe dropping from 23 squared to just 23, or from 5 squared to 5, or maybe even remove the 5s altogether. So by a systematic search, basically looking one prime at a time and seeing how far down you can go with that one prime, and then putting all that information together, you can check that the order of 10 is this thing here. So it's 2 squared, 3 to the 4th, 5 squared, 13, 23, 61, 4349, and 538411. So a couple of the primes get reduced, and the other ones stay where they are. And this product then is this number here, which is about 3, 6, 9, 12, 15, 18 digits long. So it's roughly 10 to the 17, 3 times 10 to the 17. That is the length of the repeated cycle when you take 1 over this number here. Okay, so the length of the cycle, it's the number of digits in the cycle that you have to go before things repeat. So it's more than thousands, millions, billions, trillions, it's in the quadrillions. Okay, how far the cycle extends before it repeats. And so that means that when you take the quotient of z by this m, that w that you have, well, it turns out that it starts like this, 55202985190, and then it carries on for about 300 quadrillion digits before it repeats again. So to specify that quotient, to write it out so we know exactly what it is, requires a huge amount of data. Okay, because there's this number of digits in this W before it starts to repeat. You can see that this is already overwhelming our hard drives. There's no way we can deal with this in terms of storing all this stuff. And you can see that it's gotten a lot more complicated than it did when we just had 3 primes. And you can imagine that if we added a few more primes, or maybe 100 more primes, or maybe 1,000,000 more primes, this is going to blow out on us completely. Completely going to overwhelm us. In fact, we don't have to go that far before it'd be completely unworkable to understand what this quotient is. Okay, so the difficulties with factoring a huge number like z are at least twofold that we've seen. First of all, there's the obvious problem of finding primes that divide it, because the number is so big. It's very onerous finding a prime that actually divides it. But even once we have some primes that divide it, we're seeing that the quotients that we get, dividing the big number by the primes that we have so far found and getting a smaller quotient, it's not the case that the problem is getting simpler. Because although these quotients are in fact getting smaller, they are getting more complicated. They are more complex. Their complexity is getting bigger. So the complexity is increasing even as these quotients become smaller. That's exactly what we've been illustrating with this division process that we've been looking at here, right? The complexity of the quotients goes up. And this is something that's not seen at the level of medium, ordinary level factorization. If you have a number of 300 digits and you're trying to factorize it, and you find a prime, and then you divide, well, great. Now your new quotient is a little bit smaller. Instead of 300 digits, maybe it's 249 digits. Okay, so with every prime that you find, you're happy because the quotient is getting smaller. Here, yes, the quotient is getting smaller, but that's not the crucial point. The point is that the complexity is going up. And it's not going up just, in a small way. It's going up pretty quickly. We saw that there's a huge difference between just taking the first 3 primes and taking those 6 or 7 primes that we had. Right? The complexity went, instead of having a cycle of 138, we had a cycle of 300 quadrillion. Huge difference. So, of course, eventually what happens is that the complexity just overwhelms you because you get blown out of the known universe. Okay? At some point, this number is going to be so big that you can't write it down in the known universe. You're at sea. So the reality is that it really is impossible to fully factorize z into primes, almost surely. The complexity of this problem overwhelms the possible complexity inherent in our universe. Okay, we're positing a mathematical problem whose complexity dwarfs the ability of the universe to encode a solution. That's just the way it is. Okay, this is just the reality of the world. It has nothing to do with our computers exactly, although it may appear to, but it's really a problem about the world ultimately. It's not really a problem, it's just a fact about the world. That you can write down these ridiculously big numbers, and in fact we've seen that z is not so ridiculously big, right? We've seen a lot bigger numbers than z. So what I'm saying now about z applies even more so for all of those other gigantic numbers that we've been exploring in some of our previous videos. So was Euclid wrong? Euclid clearly stated that every number has a unique factorization into primes, and now I hope I've convinced you that the number z does not have such a unique factorization, so there's a problem somewhere. Perhaps Euclid was wrong. But I claim that no, he was not. In fact, the problem is really with modern times. It's we that have the problem, not Euclid. And this is a very important point, very interesting point that I want to share with you. We have to go back a little bit and recognize that the ancient Greeks had a different approach to numbers than we do. Very different approach, because they were solidly grounded in a geometrical understanding of things. Mathematics to them was primarily geometrical. The number theory was built on the geometry. So Euclid, in books 5 to 10 of the Elements, he deals with magnitudes and relations between them. But for him, magnitudes are typically things associated with measurements involving, say, lengths or areas or volumes. So to him, a number was really more a measurement of something rather than a counting of something. Which is not to say that the counting aspect didn't play a role. It certainly did. And in fact, it had a lot to do with this idea of proportion, that if we have a segment like this and a segment like this, then we can talk about the proportion between them. We say the proportion of their lengths. But in fact, he just thought geometrically that you could divide this thing up into 3 segments, and you could divide this thing up into 4 segments, so that all of those segments were equal. And then you could say that the ratio of A to B, or the proportion of A to B, was 3 to 4. So it has something to do with subdivision. It wasn't really a counting process. In fact, it wasn't even a measurement process exactly. It's not as if you got a ruler and measured this and measured that. It was more a finding of a commensurability, finding a unit that both objects could be subdivided into. So a very different kind of approach to numbers, and that really explains why, in fact, he was not wrong about his statement about unique factorization. In book 5, he makes a definition that sort of illustrates or shows what kind of idea he has about the relative sizes of numbers. He says that magnitudes are said to have a ratio to one another which are capable, when multiplied, of exceeding one another. This is a translation of Heath of the book 5. So what does he mean here? Well, suppose we have a segment A and another segment B, and we're interested in comparing them. So how does one compare segments if one doesn't actually have a ruler? Well, what one can do is one can take one segment and multiply it by a factor. And let me show you how he might do this. So here is the segment A, and I've kind of copied it down here. Okay, so you can do that. And then if we take a straight edge, it doesn't have to be a ruler, just a straight edge. And I sort of make a little line, maybe make it solid like there, all right? So I want to duplicate this thing, or I want to multiply it. So one way I can do that is by taking some other line and duplicating, or finding a equally spaced set of points on some other line. Once I have that, then I can draw parallel lines from the given equally spaced line to this new line. So I draw this one, and then I draw another line parallel to it, and another line parallel to that, and another parallel to that. Okay, and then Euclid will know that this is also A, and this is also A, and this is also A. And then maybe this thing here is a little bit less than that, so he could say that B is less than 4 times A. So we're exhibiting the idea that's contained in this definition, that we require the segments to have the property that we can take any segment and multiply it by a suitable number, in this case 4, to get something which is bigger than the other segment. In this case, it's sort of obvious that you could just take one of B and you get something bigger than A. So any two segments that we're considering have to have the property that you can at least approximately estimate one as a multiple of the other, or bound one by a multiple of the other. So we can see the huge gap that separates us and the ancient Greeks when it comes to thinking about numbers. Euclid would have looked at one of our big numbers and said, show me the line. Construct that thing geometrically. Then I can understand what you're talking about. So he thinks primarily geometrically, and so a number is really just some kind of abstraction that's ultimately pinned down to a physical geometrical object, typically a line, but maybe a rectangle or some three-dimensional thing also. And it has to be constructed or exhibited geometrically, essentially physically, before it can be properly considered. And here's the problem, that it is impossible to exhibit both 1 and z as segments or lines. So Euclid does not have an absolute measurement. When you're talking about lines in the plane, there's no canonical unit. You have to specify a segment and say, let's agree that this is 1. And then once you've done that, well, then you can think about some other segment as being given by a number. So if this is 1, then maybe this is 10, maybe this is 23 or something, or maybe 23 and a half or something like that. But it's required to actually write down the line. And the problem is there's no way of writing down two segments, one of which is a unit segment 1, and another which is a segment representing 10 triangle 10 plus 23. We'd either have to make the segment involving 1 incredibly infinitesimally small, so we couldn't actually create it, or we'd have to create this one, essentially infinitely long, to be able to exhibit it. Right. So Euclid would have said, the game that you people are playing by these clever tricks, taking exponentials of exponentials of exponentials and so on, and just, saying, look, here's a number, is an empty game, because it's not connected to physical, geometrical reality. Now, I'm not sure if he would have said it exactly that way, but I think that's in the spirit of the way the ancient Greeks thought. And so there's no problem for Euclid in the fact that this thing does not have a unique factorization. Who cares? It's not a kind of number that he's considering anyway. So his theory is fine. It's our theory which has a problem. I think the conclusion that we're heading towards here is that of our various number systems, the one that's really closest to the spirit of the ancient Greeks, to Euclid, is that of nat, the primitive natural numbers, where we're talking just about a m-set or multi-set of strokes. Because this is somehow just a discrete version of what you get when you take a segment and you think of the segment as being a whole bunch of little units strung together. This step-by-step process of creating a natural number is, I think, just the discrete version of the continuous process of creating a line segment, sort of one unit at a time. You go there, here, and then you go a little bit further, and then you go a little bit further, and go a little bit further. The two things are really very parallel. In this way, the essential inductive nature of natural numbers is built into arithmetic. So when we were talking about natural numbers this way, well, we know that natural numbers are built up one step at a time from well, the empty set or the number 1, because that's directly what the natural number looks like and how it's been built. In the same kind of way that a segment of Euclid is built up in a very natural, direct kind of way, starting with a unit. So if we restrict ourselves to just primitive natural numbers, then our difficulties with numbers like z disappear, because z is no longer part of the story of primitive natural number arithmetic. It's just way too big. And so the theorem of unique factorization into primes holds. We recover the familiar arithmetic at the price of scaling down our expectations and so the domain in which we're agreeing to work in. We're restricting ourselves to something that's more sensible and controlled and reasonable, doesn't have all kinds of things going off in all kinds of crazy outer universe directions. Okay, and this way the kind of logic of Euclid is reflected in a logic of arithmetic. So I think we're leading to the conclusion that Nat is somehow really the fundamental arena in which arithmetic really truly takes place. And what about Num, Hindu-Arabic numerals? Well, those are pretty close to natural numbers. They're certainly bigger, but there's a close proximity. We're also assuming when we talk about a Hindu-Arabic numeral that you're actually able to write it all down. And so I think it's reasonable for us at least to hope or to aspire to extending the arithmetic which is solid for Nat also to Num. But that probably does require some additional thinking and some additional work. It's not an automatic thing. It's not an automatic thing. So we have a new conception of number here. We have a new kind of orientation to what a natural number is. And a natural question is, how do we extend that to integers? This is a very, very interesting question. We're going to start tackling that next time. And you're going to see remarkably that modern 20th century physics is going to play a very big role in orienting us in the direction of what are negative numbers. Hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.